Sure, Shakil. Go ahead.
Uh, Hello, sir.
Hi.
Yeah, Shakil,
Am
you're
I audible,
audible.
sir? Yes, sir.
Yeah, yeah.
Yeah, you're audible.
This is Shakil. So, actually, AI is a computer domain, sir, which will enable
Okay.
computers to do human tasks in a simpler or efficient, optimized way, sir.
Rightfully said, Shakil. Anyone else? Uh, are there any more volunteers for this question, or should we proceed? Okay, I'll take that as a no. So, as Shakil said, AI is something that utilizes computers to do the tasks that humans do in a more efficient or an optimized way. Slight correction, Shakil, it might not always be more efficient or optimized. Sometimes it's just meant to replicate human intelligence as well. Sometimes it's meant to do specialized tasks. It's subjective, yet, if we go to the standard definitions, we have a definition by Google here, which says it's a set of technologies that enable computers to perform variety of advanced functions, including ability to see, understand, translate spoken and written language. This is basically GPT that we are talking about. Analyze data, make recommendations. You have all got recommendation engines, right? When you're running on Amazon, right? So whenever you hit search for a particular product, all of a sudden, all the other products pop up as well that are related to it. How does that happen? How does it rank the products? So that's done by recommendation systems. When you are transcribing something, how does that happen? No, that is done by NLP. When you are building cameras to recognize people, if you have seen those new security cameras, so if you go to the systems, you have the blue box kind of thing focusing on people's heads and in their bodies, right? So that uses CNNs and other stuff. So these all are applications of artificial intelligence, but artificial intelligence can be in a way said to be a technology that enables computers and machines to simulate human learning, comprehension, problem solving, etc., as said in the definition of IBM, right? Okay, so let's proceed. How many of you guys know about the types of AI that exist, right? Okay, there's one classification that can be done in this way. You can think of artificial intelligence as the big superset of everything, right? So we have a field called artificial intelligence that has a subset called machine learning that many of you guys are aware of. It's a common misconception that it's other way around, but it's not. Machine learning has a subset called deep learning that everyone's excited about. It has neural networks, RNN, CNN, so on and so forth, which has a subset of generative AI, which is the current AI that we all interact with, be it daily on Gemini, GPT, Claude, Anthropic, whatever you want to see, right? And even in the diagram, this is something I borrowed from IBM, right? So if you see clearly, the definitions they get more specific. AI itself is written as more generic human intelligence exhibited by machines. Machine learning is written as AI systems that learn from historical data. Again, the definition got more specific. In deep learning, it becomes to mimic human brain function. Now, why have we said this? Any idea, guys? We'll discuss this coming on, but why have we said mimic human brain function? Where did this thing come from? Any volunteers? I'll take that as a no. So, this is written because the first model for neural networks suggested in 1940 by McClock and Pitt was an attempt to model at human brain. And later, when it was realized in 1957, if I'm correct, it was called perceptron. Was meant to somehow mimic how the human brain's neurons function with respect to its dendrites, axons, and so on and so forth, right? And then we have generative AI that uses deep learning models, foundation models that create original content. Not always original, but okay, it's debatable. This is one way of classification, right? Another way is the more formal way. So here we can classify AI on the basis of two things. We can classify it on the basis of capabilities. We have narrow AI, we have general AI, and we have super AI. Any volunteers to say what is narrow AI in today's world, according to what they have seen? Just any random guess would do. Anyone?
Hello, sir.
Yeah.
Maybe narrow AI. I guess just as an example of narrow AI, since it's a a very small scale and a limited set of programs. So
Mm-hmm.
I guess just I just playing game computer chess is I guess a narrow AI.
Mm,
Correct me if I'm
can be
wrong.
said. I mean, you're partially correct, partially wrong, but you can take it as maybe Alexa or Siri is narrow AI, kind of. Even GPT is now tending to become general AI, but it has not yet quite become it, as far as I'm aware, right? And let's come to super AI. I think all of us know what we mean by super AI. Shakil, would you like to volunteer for this one, or is there anyone else who wants to take the
Uh,
stage?
okay, okay, sir.
Yeah.
Karthik, Abhishek is saying only program for specific area works.
I'm sorry, could you repeat it?
Yeah, Abhishek is saying that is only programmed for specific area works.
Good, nice. That's a more specific definition, Abhishek. Nice. But that's for narrow AI, right? So what's super AI? So I'll just give you a very generic thing. Super AI is what you imagine Skynet to be, or what we imagine as Ultron or Jarvis or something. Something that can actually replicate genuine human intelligence on all levels, can showcase human empathy, can perform all kinds of tasks. It can learn and perform all kinds of tasks just like humans can. That's one way of taking it. Of course, there might be other formal definitions, and I might be slightly wrong, but this is one way. Then you have, based on functionalities, you have reactive machines, you have limited memory, you have curious mind, you have self-aware AI, AI that is aware that it is an AI, right? That it's aware of its existence. So this is on the types of AI. So let's proceed further. Now, the question comes, what is machine learning? Again, we have got two definitions on here, right? We can go through them, but again, I want to know from you guys, what do you think is machine learning? Anyone?
Guys, you can unmute yourself.
Hello, sir.
Yeah,
Uh, I guess same definition as AI, sir. Machine learning is also a domain on AI, sir, which enables we'll train the model with some algorithms and we will get the task done without the help of humans or with minimal help of humans. Anyway, you can say it, sir.
that's a good attempt, Shakil. But I think you missed one part where we have to bring in the data for
Sir,
machine
can I
learning, right?
try?
Yeah, you can try. Go ahead.
So the use of a computer to learn the data set involving a number of variables so that they can make prediction corresponding to unseen data points.
That's a very specific definition where you're reading it from the internet.
No, sir,
But
it's
that's
not
nice.
from internet. I have done the course from the ISC Bangalore machine learning. That's why I can define.
Oh, that's nice. That's nice. Yeah, that's a cool definition. That is a very specific definition and a correct one, I must say. So yeah, that's what basically machine learning is. If we are supposed to borrow again some other definitions, IBM defines it as enabling computers and machines to imitate tasks the way that humans learn and perform them autonomously, improve the performance accuracy through experience and exposure to data. Uh, with respect to UC Berkeley, they define it as leveraging data mining to identify historic trends and inform future models. We'll share these slides with you. So there's a cool visual by R2D3 for introduction to machine learning. So it will, for those guys who do not have any exposure, it will keep them in the loop somewhat, right? You can check it out later on, right? So now that we have delved on this, let's focus on types of machine learning. Broadly saying, machine learning can be classified into four types. You have supervised learning, you have unsupervised learning, you have semi-supervised learning, and you have reinforcement learning. Now we have a chart that's visible there, and everyone can see that. But let's go beyond it. Anyone would like to define? Okay, I think all of us know what supervised learning is, right? Supervised learning is where you have data that is a labeled data set. What I mean by labeled is your target variable for each example that you have the specific target variable allocated for it. For example, if we have a bunch of images of animals, specifically cats and dogs, we have labeled each image as a cat or a dog. So that would make a labeled data set. When you utilize a labeled data set for training a machine learning algorithm for a classification or a regression task, as is visible in this flowchart for continuous or categorical variable, which by definition goes to regression or classification, then you are doing supervised learning. Let's come to unsupervised learning. Anyone would like to define what unsupervised learning might mean?
So actually, it's not unlabeled data sets. So we will work on the unlabeled data sets.
Mm-hmm,
So like you said, we don't know the target values.
mm-hmm.
Yes, so I guess this works. I guess so.
Okay, yeah, that's a method to define. That's correct, Shakil. As Shakil said, unsupervised learning one works on unlabeled data. It's if I draw an analogy, it would be kind of like you have a small kid, okay, and we gave the kid a couple of blocks to play with. Some are cuboids, some are balls, some are, let's say, pentagonal pyramids, some are tetrahedrals, and so on and so forth. And they are of different colors also. Now, we haven't taught the kid the math yet, right? We haven't told it, okay, this is a cuboid, this is a circle, this is that, this is that. But what we often observe is the kid will usually classify them into different piles. At least we can ask the kid to do it. This is similar to what we do in unsupervised learning with respect to machine learning algorithms, right? One of the biggest example for this is the k nearest neighbors, where you first initialize random k centroids, and then you try to center your data according to them. And in each iteration, you update the centroid unless you have a tolerance level reached, after which you finally give out the grouping, right? So that's kind of an unsupervised learning. You just have data and you're trying to learn patterns through it. Now, what's interesting is semi-supervised learning. What do we mean by that? That's an interesting one. Anyone for that one? Uh, would anyone would like to take this one? Okay, I'll go through this. I think most people are not aware of it. So, semi-supervised learning works something like this. You have a mix of labeled and unlabeled data. Now, the question is, how does the model work with this? Answer is somewhat like this. Given an initial data, you train the machine learning model to run through it to learn the labeling, right? Whether it be classification task or clustering task or whatever, right? I'm just explaining for a classification task. You make it learn the labeling. Once it has learned it, on the unlabeled data, you make the model predict the labels, and then use that pseudo label data, we can call it, right? For again training the model, and this is done iteratively. Where this is applied for is in many real life scenarios. For example, you are a radiologist, right? You want to predict a model, you want to make a model that predicts, okay, where are cancerous tumors in that particular chest X-ray, right? Now, a radiologist has only so much time. He can't be asked to label 10,000 X-rays, and we all know ML models are only as good as their data and the amount of data they are trained on, right? Because they are supposed to generalize. So the question comes, what do we do? Here we use semi-supervised learning. The expert labels the few X-rays We use those few X-rays to predict on other unlabeled X-rays, and then we keep on going. And we again feed the same data to the model. It again predicts something. Again, we do the same thing until it finally learns the patterns, right? And then we come to reinforcement learning. Now, this is something that kind of really mimics how biological beings learn, how we as kids learned, how our pets learn things. It's like this. Suppose you have a dog, right? Now you want to teach the dog tricks. So what do? You let the dog do whatever it does throughout the day. If it randomly does something that is good, right? You give it a treat. And if it does something bad, you try to punish it, or maybe you do nothing. You do either of the two. In long duration, through the repeated feedback and the memory the dog has, it learns what trick it has to do to get the treat and what it should not do to avoid the punishment or avoid getting no treat, right? This is what reinforcement learning is. You have an agent, right? You have a state, it transitions to different states. For each state, you get a reward or you get nothing, or maybe you get a penalty. And the overall optimization goal is maximizing the reward. Now, this is utilized in many tasks. You can utilize it for training driverless cars. Another utilization is for training upside down flying helicopter. You can check out the video. It's by the OG of this field, Andrew Ng. They did it at Stanford. They tried to teach a helicopter to fly through reinforcement learning, and it learned how to do tricks and how to fly it upside down as well. So yeah, that's one crazy thing, right? And basically, it performs on the basis of feedback and the memory the model has, right? So this is something about the types of machine learning we have. Okay. For supervised learning, as I said, there's many application. For example, a cat dog classifier for your basic ML project, to a housing price predictor, a good housing price predictor. That's the first starting project of any Kaggle solver, or maybe the Coursera Android course solver, right? Or you can basically supervised learning has applications anywhere and everywhere, right? With unsupervised learning, it's good for categorizing different data, right? For identifying outliers in data, right? And for with semi-supervised, it's applicable in more practical scenarios, as I said, medical imaging, lane finding on GPS data, it's written here, text classification, so on and so forth. And reinforcement learning for driverless cars, for making helicopters fly upside down, and so on and so forth, right? Reinforcement learning currently is more of a research-based field, but yeah. So let's move along. Let's delve into how this all started. So we come to the history of AI and ML. If you see on the right, the image in white, right? Can you guys see my cursor? Guys, can you hear me?
Yeah. Yeah.
Yeah, Karthik.
Okay, sure. So if anyone would like to identify, what do we call these? Because I think a couple of you are familiar with all this stuff, right? What do we call these things?
These are vectors, I guess.
It is stored in a form of a column vector, yes, or maybe a row vector. But what is this? These are weight vector, right? Specifically weight vectors. These are weights. And that theta thing, it's a bias, right? It's the bias is weight vector, but the bias value is fixed at input of 1. So if you try to remember it clearly, this and this phi thing, what does it represent? Anyone for the phi? What do we mean by phi here? That's phi. Okay, I'll explain it. Phi represents activation function, right? With respect to the original paper they published, it was, I think, sort of a signage or tannage activation function. Basically, it was a sigmoid activation function. It was meant to do that, but practically you can't train on it because sigmoid is the irregular function. It suddenly jumps, right? It's broken. So that's why you take sigmoid or tannage as an approximation of sigmoid. So basically, what happened here is you have got different inputs, right? X1, X2, and Xj. They multiply through the weight vector. You have got bias. It's summated here inside the neuron. It's passed through an activation function, and the output is received here. Now the question is, how is this thing trying to replicate what we have as a biological neuron, right? How is the McClock-Pitts model trying to replicate it? In biological neurons, if you see any image of it, it has dendrites, it has an axon, and it has some nerve endings uh, below the axon, right? So what happens usually is each neuron receives inputs in form of chemicals or otherwise or electrical pulses from other neurons. Now, based on these inputs that it receives, it decides whether to fire or not, right? Which is why I talked about using a sigmoid function with a threshold value, which will determine whether this neuron will fire or not based on its output being 1 or 0, based on these outputs being 0 or 1. But to make it more applicable for real life scenarios, these are continuous outputs. This threshold function is not exactly sigmoid, but a tanh or a signage function, or maybe you have got other functions as well. You have got ReLU, you have got leaky ReLU, you have got a lot of activation functions, right? And this output, it can also be a continuous variable for modeling in modern neural networks. But if you are trying to model a biological neuron, you'll have to give these inputs at 0 or 1. These weights might vary. The activation function threshold will be there, and it will be 0 or 1 as the output. Because that's how a normal neuron works, right? So 1943, we have Walter Pitt and Warren McClock published a logical calculus of the ideas immanent in nervous activity. Crazy name, but this thing introduced the McClock-Pitts model, which started the whole machine learning thing, right? Another interesting thing is one of these guys was self-taught, specifically Walter Pitt, and Warren McClock himself was a physician, right? So that's just a crazy fun fact for it. Okay, and let's move ahead. So, how many of you guys realize this guy? Please don't read the point, but try to see if you know this guy, right? Any of you know Alan Turing? Okay, what
No,
is he
sir.
known as? Okay, I'll brief you it. Alan Turing is called the father of, any guesses? He's called the father of modern computer science. Okay, why is that? Why did Alan Turing become so special? Why is he called this? Okay, for two titular reasons, as I am aware of. One is, if you guys are aware, 1942 World War, Nazis were using something known as an Enigma machine, right? It had the Enigma code, and he was the guy who built a machine, a first of its kind, that was kind of supervised learning to break
So,
the Enigma code. He was,
Karthik, we have a
yeah,
question here. So,
yeah.
Saket is asking that um, this is old, and why don't we use modern artificial neurons?
I couldn't get the question. Can you frame it better, Sakib? Because from what I'm trying to tell you, these, of course, these are not used today. This I'm just walking you through the history of AI and ML, so you know how the field came about. Once you do know how it came about, of course, the neurons that we use today are very different. We have got different activation functions. Even the layers are working differently. You've got kernels and CNNs, right? In LSTM, you've got memory unit cells, right? And for transformers, the architecture is totally different. Of course, that is there. So I'm just walking you through the history of it, right? So I think that should answer your question. So Alan Turing was the guy that built the machine. It was called Christopher. That could break the Enigma code. That's one thing. Second thing, he devised something known as a Turing test. That is one of the most popular tests to test if something has true intelligence, so to say. This diagram is a small representation of it, but if I basically break it down, it means that on one side you have a computer, and on one side you have a actual human, and there will be a tester who will be an actual human again, right? You can call it interrogator, questioner, whatever, right? Now they'll talk with both or do whatever activity with both, and they'll have to differentiate which one is a robot and which one is a human. If the robot can convince, if the computer can convince the interrogator that they are the human, then that is denoted as an idea of what is that bot has some form of true intelligence. That's one way of saying it. Okay. Moving along, we have in 1956, Dr. John McCarthy, this guy is also called as the godfather of AI, right? He coins the term artificial intelligence that we use so much today at the Dartmouth conference, right? In 1957, you have got Frank Rosenblatt, who created, who actually created the, okay, so in 1946, if we are talking in 1943, right? That was a theoretical implementation that, okay, this is something that can be done. Rosenblatt was the guy who actually did it. Okay. He was a psychologist by profession. IDK, what psychologists were doing with machine learning at that point in time, but okay. And this led to one of the foundational moments for modern neural networks, right? If you move ahead in 1967, we have nearest neighbors algorithm, or as popularly known as K nearest neighbors, introduced in the nearest neighbor pattern classification by Dr. Thomas Clover and Peter Hart, right? And if we just briefly walk through how it worked, so K nearest neighbors utilized randomly initialized K centroids, right? Now for each centroid, you go ahead and for each point in the dataset, you try to determine its closest to which of the following starting centroids, right? Whichever is closest to, it's allotted to its cluster, right? So you have got K clusters now. For each cluster, you recompute its centroid, and then you do this process again and again and again until the positions of centroids stops to change, ideally. That's one way to do it. Now, between this, now we are also heading to a period of AI winter. Not much work was done here. Neural networks and perceptrons introduced in 1957 got a lot of excitement, but little potential was seen through them because of long training times and so on and so forth and limited ability to learn, right? So we go ahead and we go ahead to 1979. Here we have Stanford Cart. This was one of its first kind of driverless vehicle, so to say, right? It could tackle obstacles on its own. You can check out this video, right? I've added the link here and we'll share the repeat and you can check out the video. It's a crazy thing. Uh, a unique thing about it though is that this cart, its successful navigation took 5 hours to cross just 20 meters of the room, and it would move in 1 meter lurches, pause up for like 15 minutes, and then process the visual data and plot its next move. Right. This was the starting of the Stanford's robotic laboratory. Now it has more crazy stuff, but yeah. Okay. In 1986, we have the comeback of artificial intelligence. We go here and we have coming of back propagation. I think anyone and everyone who has worked somewhat with machine learning will know what back propagation is. Would anyone like to define it for me? Basically, just what it does. That would do. That would suffice. Come on, guys. It's supposed to be an interactive session. Any volunteers?
Yeah, I think Saket is typing. Just wait a minute.
Okay, cool.
In the meantime, guys, is the pace okay? Are you able to hear? Is there any problem?
It's fine, sir.
Okay. So Saket is saying training neural networks where error is propagated backward.
Okay, that does summarize it, Saket. And how is it done? Would you like to brief on it, Saket? Or should I take that part?
So he is typing. So Saket is saying that through the network to update the weights and minimize I value, I guess.
Okay, that's what it does, Sakib. But how it does it is basically, I think all of you would remember your 12th and 11th class maths and perhaps college first year maths, where you learn about partial differentiation, right? So what it does, it has a loss function. Okay, so output and the desired output, you compute the error between the two. You make a loss function out of that error. It can be error squared, it can be summation of error squared, mod of error squared, mod of errors, mod of sigma of errors, so on and so forth, right? And then you do a partial differentiation of this with respect to the weights that contributed to output. Again, for that each weight, you bring it to its original neuron out here in the blue layers. Again, you do the partial differentiation, you bring that error contribution here. Again, you do it and you bring that error contribution here, effectively updating all the weights of the network, right? This works on the assumption that any error that happened has some contribution from everyone, right? So basically, use differential calculus to propagate the error back. Now, this was a really crazy thing back at the moment because it allowed faster training of neural networks. It solved the XOR problem that networks were not able to learn XOR effectively and other limitations identified the mix by the I'm sorry, Minsky paper, right? And this is where we really unlock the potentials of DNNs. And here is where you again have thrust into neural networks. Into everyone is like, okay, let's work on neural networks again. Okay. And if you go ahead with this timeline, you see people coming up with CNNs, people coming up with DNNs, people coming up with RNNs, people coming up with LSTM, people coming up with all sorts of networks, right? So this was one standpoint. Another crazy standpoint that in history of AML for public significance, so to say, happened in 1997. You've got IBM's Deep Blue versus Gary Kasparov at 3.5, 2.5. Now, anyone who knows chess, I think, would understand this as there was a game of, I think, 6 matches, if I'm correct, or maybe it's five. And basically, Deep Blue won against Gary Kasparov, who was the reigning champion at that point of time since quite a few years, right? And this titular defeat was a moment of machine priding over man. That okay, we have defeated the grandmaster of chess. Of course, you might also get conspiracy theories that okay, Deep Blue was helped out or whatever or not. But I'd like to believe that it was an original win by Deep Blue. Okay, and that was one thing. So this was crazy. And another thing to note about this is that this was the second match. The first match that happened between them was 10 years back, if I'm correct, in 1980s or something. Okay. And back then, Deep Blue lost with, I think, 4-2. It was a six-match series. Yeah. And okay, yeah, it happened in 1996. Sorry, 1 year back, 4-2. And in 1997, rematch, 3.5, 2.5, six-match series. Deep Blue wins. Okay. This was a titler moment. So moving ahead, we come to CNNs. Now, these are introduced in the paper gradient-based learning applied to document recognition in year of 1988. Now, would anyone like to tell me why are CNNs important? Why are we discussing CNN specifically? Why do I have a separate slide for them? Any volunteers?
So, CNN is a like a base algorithm for image classification, and and some process on images.
That's a good guess. Okay, question. Before we delve into how CNN works, what else can CNNs be used for? I'll just go through a brief explanation and I would like an answer at the end of it, right? So what CNN does is assume you have an input image. Okay. I think all of you guys can see my screen here, right? Sorry, just give me a moment. So assume you have an input image. Okay. So given the input image, you have each input image can be broken into three images: red, green, and black. RGB. Red, green, and blue, right? RGB, right? So you've got three images here. You pass it through initial feature maps, initial convolutions. These are passed through kernels. So each kernel basically what it does is you've got these. What do we mean by a 3 cross 3 kernel, right? So you've got a 3 cross 3 grid with random weights across it. Okay, and it's multiplied across this purple thing across the length of it. You might have heard the term of padding. Padding refers to what do you do at corners. You add additional cells that have weight that have the value as one here. That's one padding. Do they have value zero here? That's zero padding. Okay, till what depth are you applying padding, so on and so forth, right? And stride length basically means how fast that matrix jumps over. Basically, what this means to do is these feature maps or kernels, they try to mimic how humans see, kind of. Matlab, they don't, it wasn't meant to do that great, but matlab, they try to do that. Okay, so my question is, how do you think we identify a cat from a dog, right? We look for ears, we look for eyes, we look for specific shapes, right? So the first stage of feature maps, the initial feature maps, they look out for edges. There might be a feature map that might be looking at the image horizontally. Okay, these are the horizontal edges. There might be a feature map that's focusing on the vertical edges. There might be one that's focusing on diagonal and so on and so forth, right? In the second stage of you keep on doing this, right? So in the second stage of feature maps, you've got feature maps identifying different object parts. And this all is done via backpropagation while training them. They slowly learn to identify that. How do I know that how do we know that they are identifying them? So that's basically done by whatever info is coming to them, right? After passing through those feature maps, whatever output comes, you can just pluck it out of any CNN, right? You can find the code on GPT or something. And what you'll see is that these feature maps are identifying specific things. At first, they identify edges. At second, they identify object parts. So, for example, this would be edge of a cat's face. This would be the cat's ears, eyes, and the third stage would be the cat itself, right? In this case, as there are multiple objects, so this will be multiple objects. So initially, it's passed through kernels, and at last, it's passed through fully convolution layers, fully connected layer. I'm sorry. Fully connected means each of these feature maps is connected to each of the neurons present here. Okay, there's no optional connects, right? For example, in these kernels, if weight suddenly becomes zero, so any sort of cell that's multiplying here, any sort of value that's multiplying here to zero, its effective contribution after sigma goes to zero, right? So basically, it's disconnected to this layer. So here, everything is connected to everyone. Okay, that's given to you can say logistic regressions activation function, right? Sigma activation function, so on and so forth, for depending on the classification task you have. So that's one way you can see it. Okay. So CNN can be also said to sort of summarize the information, right? So as I've dropped you a hint, I'd like to ask you again, what do you think? What else task is there that CNN can be used for? Anyone? Guys, can you hear me? Hi.
Yes, sir. Yes, sir.
Okay. Okay. So what else do you think CNNs can be used for?
So it can be used for detection or classification. So like image detection, image classifications, or these are the things. These are the few things of applications of CNN, sir.
Okay, okay, Shakil. Let's do this. Let's do this experiment. When we multiply a kernel with the initial matrix we have, right? When we are doing max pooling or main pooling, right? So whenever we do this, what's happening to the information? Will you say that the information is getting less, or at least that particular feature map, it took a 9 cross 9 thing and it converted into a 3 cross 3 or a 4 cross 4, right? So when it did that, it tried to sort of compress the information. Am I correct?
Yes, sir.
Where do we compress the information again? Okay, I'll bring it to it. Summarization
Uh,
tasks. You can use CNNs for summarization tasks as well, although with not that much fluency and accuracy as you might experience with the modern day transformer architectures you have. But CNNs can also be used for similar tasks. You just need to prepare the embeddings for different words, tokenize the words first, prepare the embeddings, pass those embeddings through the CNN, train it, right? And then whenever you provided new data, it will summarize it. Basically, it will work like that. Although mostly CNNs, as you said correctly, they are used for image classification, video mapping, and all sorts of these tasks. Okay, that's nice. So now let's move ahead. After CNNs, what do we have? Right. So, yeah. After CNNs, we have 2006. We have this guy. He is Dr. Geoffrey Hinton. He coined the term deep learning. Okay, that we use nowadays very frequently. This is also the guy who warned us of the power of AI and that maybe humans are not doing the right thing or something, right? And in 2009, you have ImageNet, which also held its Titler competition, which is mentioned here in its name, ImageNet Large Scale Visual Recognition Challenge from 2010 to 2017. It was the first of its kind dataset that had high quality labeled images in millions of numbers, launched by Fifi Lee and her team. In 2010, you got AlexNet, which was run by a guy known as Alex Geoffrey Hinton and another guy, which could achieve just 18.6% error on the ImageNet dataset for classifications. This was a great benchmark at that point of time. It was almost a waterslide victory that it kept for a couple of years with it, right? And after AlexNet, you've got other networks. You've got ResNet by Google, right? You've got DenseNet. These are kind of CNN architectures that were modified. Again, if you see in AlexNet, AlexNet is also kind of a CNN architecture, right? Just for this classification task. So this was there. Come along. Now we come to year 2017, right? You've got transformers. Which transformers are we talking about here now? Are we talking about Autobots and Decepticons? Are we talking about Optimus Prime? Yeah. I mean, you all like those movies, but no, these are not the Transformers. And I'm not scared to admit it, but initially when I delved into this field, since I'm from an electrical engineering background, I used to think, okay, Transformers means this guy. This big machinery that translates low voltage to high voltage, that's used in distribution networks and everywhere. Like, it's not that as well. So what is Transformer, right? What was introduced in the paper, Attention is All You Need, which is, by the way, a very catchy title, done by Google researchers, right? Why did this thing revolutionize everything? Okay, to understand that, we need to go a little bit behind. Now, Transformers revolutionized the field of natural language processing, right? How do they do that? What did they exactly do? So, if you go a little back, in NLP before Transformers, you had two very popular architectures. You've got RNNs, recurrent neural networks, and you've got LSTM, which is a special variety of RNN, long short-term memory recurrent neural networks, right? So what are these? Okay, so an RNN or a recurrent neural network has an input, it has a hidden state, and it has an output. It might be sequence to sequence, as in you feed a sentence, you get a sentence out. It might be sequence to word, as in you feed a sentence, you get a word or a classification out. It might be word to sequence, you feed specific word, you get a summary out or a story out, I don't know. And it might be word to word also. Okay. So what it does is for so let's say you are trying to train it on a sentence, right? So you pass the different words of the sentence at different instances and you get the different outputs here, right? And for the initial state of the sentence that you pass, it also goes here as a hidden state, right? So generally what happens is the hidden state is the actual output itself without any modifications in the original RNA. And it goes here and you provide the next input with the hidden state. It combines with some activation functions. It again goes to next hidden state. You get an output out here and everything. So when you are backpropagating it in RNA, it's called backpropagation through time. You go through different timestamps because you can call this time instances as well of the input, right? Because for a single input, you're breaking down into different time instances. through the same network, right? So imagine this as a single neuron, but every time you feed it for a single sentence, you're every time you're feeding it a new word and you're feeding a history of the old word as well that's coming through W, right? So what it did was it had a sort of memory. Okay, good. It has memory. It can remember. In sentences, we do need to remember. What's the problem? Problem is vanishing gradient. As I said, backpropagation works through partial differentiation. Now, what happens if I do continuous differentiation of something that's very small, right? Or very large? Okay, so if your slope is very large and if it keeps on going larger, you might get exploding gradient. You might get erratic weight updation. And if something is small, you take a del of it, you make it even smaller, again gradient, even smaller, right? What's happening is you're multiplying 0.01 by 0.001 by 0.00001, so on and so forth, until when it reaches the first layer, the effective weight update is zero. So there was the problem of vanishing gradient as well. All these things led to the singular problem that RNNs had a very short memory span because of the thing that after 4 words, the gradient vanishes and the update is comparatively less. So it's remembering, let's say, only the last 4 words, right? So to resolve this, we have something known as LSTM. LSTM is the long short-term memory network. So if you see something, the upper line, that's your long memory, right? And this lower line, this is the short-term memory thing. So here it decides what to carry outwards, right? Here you put the actual immediate input. Here you put the short-term hidden state. You create a short-term memory from whatever from that short-term thing. You update it to a long-term memory. So like this is the long-term memory that you carry out, right? So you update it here. You update the long-term memory here. You take the short-term memory. You provide it as output as well as the hidden state for the next layer, right? And you keep on doing this. So what it helped was it helped the RNN now remember the long-term stuff as well, right? Basically, in rudimentary word set. After this, we have something known as transformers, right? So even in LSTMs, at very large contextual durations, they would start to forget, right? And this bottleneck was there. Another bottleneck that was present in RNN was sequential thing. So if you notice something, RNN is sequential. It will go here, then it will go here, then it will go here, then it will go here, right? So if a process is sequential, you need to do it step by step. You can't parallelize the things. We can't run all these things simultaneously. So we also need to resolve that kind of stuff. So we have a transformer. Now this is the transformer that I'm talking about. This is the architecture that was discussed in the attention is all you need paper, right? So what does it do, right? So it has basically what is something known as a self-attention mechanism, and it doesn't have only one self-attention head. Call it a call the mechanism as an attention head. It has multiple heads. So each head learns different things. Each head has a key, query, and a value pair, right? So query is for so what it's trying to do is it's allowing each word in the sentence you're inputting its value to be updated regardless of its position and with respect to all its neighbors simultaneously. Okay. Technically, not all you have a contextual window, which I think 8012 for GPT and stuff, right? But it works like that kind of thing, right? And in the value pair, you have its the words representation, the current representation, and the key pair is sort of a mapping to it. So you create a product of these three things and you try to update the value after each multi-head attention thing, right? You keep on doing this through different attention heads so that different heads learn different notions in the data. Okay, one might learn the sentence's grammatical structure, one might learn the satire intended, right? One might learn the literal meaning, one might learn the philosophical meaning. I'm just guessing here, but this is kind of how it works, right? So how we are solving the problems here? First, We are solving the problem of long short-term memory by making it so that each word has self-attention and its value, its vector value. Okay, value. What am I talking about value here? Why am I talking about value? Right. You can't feed a literal word to a model, right? You'll feed a vector. You'll feed a vector embedding. That embedding will be multidimensional across various dimensions, various semantic, syntactic dimensions of that word, and it will represent what does that word numerically mean. Okay. For example, just to make it sound some more sense to you, a king will be more near to the embedding of a male, and a queen will be more near to the embedding of a female, right? So this is how embeddings work, so that it can learn relational data. This is how embedding is supposed to work. Imagine a multi-dimensional graph sort of thing, then different words plotted out everywhere across different syntactic axes of gender, of role, of action, so on and so forth, right? There's just different axes, million, multiple of them, right? So it allows that value of that particular word to be updated with respect to the sentence that is feeded to the model independently of the word's position. So a word later on is given somewhat equal importance as compared to the word earlier on, right? So we can have more meaning to it. Okay. So you don't have the problem of long short-term memory here. Now we come to the problem of parallelizability, right? So you've got multiple attention heads. Okay, you're not just asking one attention head to learn everything. Each attention head can be parallelized, right? And this makes sure that you learn different relationships simultaneously. This makes the whole thing faster. For detailed interpretation, there is a couple of videos I would suggest you to check out. You can check out the videos by Andre Karpathy, right? He has walked you through Transformers architecture and stuff. You can check out by Three Blue One Brown on how does GPT and how do transformers work. There's a couple of other GitHub links as well, and I'll share you those so you can have a much better understanding of this, right? So this was kind of for history of AI and ML. Any questions at this point, guys?
Yeah, you can unmute and say it in the meet, as well as you can type it in the chat.
Actually, sir, can you explain this architecture, like how the transformers are working in a, you know, more in a simpler way, sir? Because it seems a bit complex actually. So I would like to
Yeah,
get a better understanding on this topic, sir.
yeah, figure seems
Okay.
too confusing. So Karthik, can you please explain it in a simpler way?
Okay, I'll try to explain it again. Okay. Any sort of word that you feed to a machine, it has to be a number. Would you agree with me on that?
Yes, sir.
It has to be some sort of number. Can a single number suffice? Can you linearly plot words?
No, sir.
So you have to have a multi-dimensional vector, right? Let's suppose you have a column vector or a row vector. Each are interchangeable, it's just a transform, right? It goes across various dimensions, right? So this you can consider it as the value vector, right? So it holds the semantic meaning of that word. You might initialize with some value vector that you obtained using earlier embeddings that are publicly available, right? Now we come to the key vector. Now, okay, imagine it like this. The query vector, it represents the specific question about the current word. For example, if the word is it, the query is asking what does it refer to in the context of this sentence, right? The key vector, it's like keyword or titles, right? So each word has a key that advertises its identity. Okay. And the value is the semantic meaning. Value is the actual meaning. Query is the contextual meaning sort of thing. And key is you can consider it sort of an identifier. After this, for this you do scale dot product attention, which basically is a sort of a dot product multiplication between the three. I can't recall the actual multiplication that used to happen, but you can check it out. But I think it's k cross q plus v or something like that. You basically update the v again, and after the scale dot product is mentioned across different attention heads, you concatenate it, you linearize it, and you create a single updated value for the particular word. Were you able to understand it more clearly right now?
Yes, sir. Yes, sir.
Okay. Basically, you're trying to learn the meaning for that word. Now, this is not just done once. Once that meaning is learned, okay, you have a sort of a feed forward neural network thing, right? And what happens inside that is now each word of that sentence, I should not say word, because when you're passing things to the transformer, you're passing tokens. Tokens are much smaller than words. Okay. So each emoji can be considered one to three tokens, right? Backslash n is a one token, right? That you use for new line character. The word, let's say you have a word discard. So it might have two tokens, dis and card, right? The tokens are generally 3 to 4 characters long and they have their own meaning and stuff, right? So you've got tokens, okay? And each token, it goes through the multi-headed attention, it updates its values, then it goes through a feed-forward neural network where everything is connected to everyone sort of thing, right? And after passing through different, it's kind of imagine it like a dense neural network, right? And it outputs the same dimensions again. Okay. So you put n cross n, again it outputs n cross n or m cross n, right? Because you are inputting m cross n because the number of words and number of dimensions across which you represent them might be different, right? So that happens. And then this is done once. Again, that updated value after feedforward networks again is passed through self multi-headed attention. Again, you get updated values. Again, you pass them to feedforward network. This is done so on and so forth until the end, right? And if you, I think, for explaining it better, you should check out Hebrew One Round video, right? Initially, I also checked out that. So after that, finally, it predicts the networks. Basically, how you train a transformer is you give it the first 5 words of the sentence or first few words, right? And then you ask it to predict the next word. And for each word, you keep on doing this. Okay. So it also learns basically, if you know about transformers or LLMs, right? They are called as very good next token predictors. Am I right?
Yes, sir.
So you're trying to teach it how to predict the next token. Okay. And this is done through the multi-headed attention mechanism where each word's embedding plays a significant role. Then you feed forward it through a dense neural network. Again, you do the same thing. And we do this for multiple layers. Okay. And finally, you ask it to predict again through a feed forward neural network that, okay, now tell me what should be the final embedding value, right? And it gives out a final embedding value. That embedding value is de-embedded to the literal word that we have, and that word is outputted. So basically, what happens when you interact with a transformer, let's say you interact with GPT. Okay, GPT is graph like a transformer, but let's imagine you interact with a normal transformer. You give it a sentence, it takes the sentence, it breaks them into tokens, it breaks the tokens into embeddings, it inputs the embeddings, it passes them through itself, right? And based on those embeddings, it predicts the next token that it should be, de-embeds that token. Okay. It gives out the output of it gives out the first token of output. It again appends that first token of output to your input, again passes the whole thing, again does the same thing, the second token, so on and so forth, till its token limit is reached or till some stop character is achieved as the de-embedded value, and that's where it stops to give your output. Was I able to give you some more understanding? I know it's not very clear right now, but uh, was the
Yes,
understanding
sir.
better? Or
Yes, sir. Yes, sir. It was, yes, sir.
okay. I would really recommend because like this is a sort of heavy thing, and you should really check out some representation. I'm sorry, this is not. I really wanted if this could have been done in sort of a way where I could draw and tell you, right? Because with a diagram and with just a cursor, I can tell you only so much. But if you check out the representation by Three Blue One Brown, right? or Andre Karpati, you'll really see how things are working around. What do you mean by K, Q, and V? Like I think Free Blue now is a 7 lecture series, and it will tell you in depth what does transformer mean by itself. Okay, do check that out. Okay, any more question, guys? From the previous part, I explained any other sort of algorithm you might want to talk about or something before we proceed further. Okay, I'll take that as a no.
Yep.
With this, we come to generative AI. Okay, and at this point, I would like to invite my fellow presenter for the day, Rishabh Soni, for taking over the session from you. He'll walk you through agentic AI and generative AI. Before he takes the stage, I just want to interact with you for a brief moment and ask you, okay, what do you understand by generative AI or agentic AI? Any volunteers? Okay, let's go for generative AI first. What do you understand by generative AI? Guys, any volunteers?
So generative AI is like it generates contents, like contents. It can be a text, it can be images, or it can be anything. So Gen AI, just it is trained with like larger data sets. So as you said, it predicts, it does everything. So I guess ChatGPT is a huge example for generative AI.
Good, great. So, what do we mean by agentic AI then? What does agentic AI do? I mean, of course, this is a session and we'll tell you about it, right? The later part of session is only about that, right? But what does agentic AI mean? Okay. So, I'll
Guys,
just give you a
there
very
is no need to frame a right answer. Okay, if you can just describe in a simpler way, you can describe it. Go ahead, don't be shy. You can type it in the chat as well.
okay, before we proceed, I think we have a really cool analogy for it. So, imagine you
Saket
have
is
a raw
saying,
agent. Yeah, okay,
yeah,
Saket. Yeah, go ahead. Go ahead. Go ahead.
Saket is saying that which can make decisions.
Cool. That is a one-word definition kind of for it. A cool analogy to consider would be generative AI is someone who needs a handler always, right? Matlab, you need to tell it what to do. You give it a prompt, it does react to that. Whether it be a VO3 that generates videos, you give it a prompt that, okay, generate this video. Or whether it be GPT, you generated and give it an input prompt that gives you out an output prompt, right? And so on and so forth, right? And with GPT and everything, there's also a limitation that they can't. Now they can because now they're using different architectures. Now they're using sort of RAG plus other API calling and so on and so forth, right? But they're also limited to their training data and stuff, right? So what does Agentic AI do? Agentic AI is kind of like a raw agent, okay? So what it can do everything. It can act independently. It has very specific goals in mind. Generative AI is kind of generic, right? It has autonomous action and decision making thing. It ideally should have. It should be capable of setting its own goals, etc. It should be able to do its work with minimal insight. Okay. So that's one way to say it. But how do we interpret it in real life? Right. So how we interpret it in real life is agent is someone who has agentic AI is a combination of LLM with different workflows. By workflow, I mean the agent's prompt passing through specific stages and those specific outputs coming back to it, and it's deciding on the basis of those things. It has access to specific tool sets, right? So there's a tool that can search the web, right? There's a tool that can call someone up. Okay, so let's imagine you have a voice calling agent. Okay, So that agent will have access to a database, right, to store some stuff regarding that user, right? It will have access to LLM APIs that can transcribe as well as voice dictate the data, because when you're talking to a voice calling agent, right, when you're talking to a chatbot, you're telling it something in human words. Now, those words, that audio needs to be constructed into text because LLM inputs text. So you need access to that kind of API, right? You need, whenever LLM generates something, it again generates text, which is then converted to words through text to audio models, right? So you need a text to audio model as well, right? Then you need a sort of a RAG architecture implementation as well. You need a knowledge base where okay, it can refer to these things that okay, I'm a chatbot of this and this company, and these are the company policy guidelines, and I'm a chatbot meant to assist customers with let's say loan fraud. Okay, so I'm with specific bank, I'm assisting with loan fraud. So each bank has specific guidelines. So the knowledge base will contain those guidelines. So the agent should be able to go through those guidelines as well. It should be able to retrieve that, okay, this specific document is referring to what the customer wants. Okay. That okay, customer is asking that so and so guy defrauded me through so and so mechanism, right? So that so and so thing, right? That is what agent should be able to recollect. Apart from the text to voice to text and text to voice and the LLM mechanism, right? It should be able to handle turn taking. What do I mean by turn taking? Okay. When we are normally calling, right? When we normally talk on call. So when I'm calling to you, you're calling to me, we are talking, right? I say something, you listen. You say something, I listen. I'm saying something, you cut me in the middle. Again, you start saying something, I start listening all of a sudden. Then I start saying something, I cut you in the middle, so on and so forth, right? This is very normal for us humans. How do you do this in agents, right? So you do this by turn taking mechanisms. You make it understand that, okay, now it's speaking. Now the user again started to speak, pause, take what user is saying, right? Or most modern bots can't do this. Always some can. Okay, for example, if you use Apple's phone, right? You have a chatbot, right? So they don't have a chatbot exactly. That's a chatbot. That's not an agent. So obviously that's not an agentic AI. But you have places where agentic AI is implemented in chatbots. At least in foreign you have. I think Airtel also has it for the customer care. I'm not sure. But agent should be able to handle turn taking, right? So this is just in a calling agent. Imagine you have an agent to do bank tellers work. Imagine you have an agent to do teaching. Imagine you have an agent to, I don't know, to handle machining tasks, right? So for all these things, you need various kind of tools that it needs access to, various algorithms. You need workflows. Why do you need workflows? Workflow is required because, okay, what is a workflow in a calling agent, right? The workflow is simple. I am talking it on call, right? Whenever I talked on call, first it passes through a audio to text model, right? That audio to text model transcribes the thing, right? When it has transcribed that thing, the transcribed thing goes as a post request to my server of the chatbot. At that server, it goes to an LLM as an API call again. That LLM gives out a text output. I'm talking about a cheaper version. In the modern version, you've got LLM directly giving you voice output, but LLM don't do that. LLM gives out text output. That text output is goes through uh, text to audio model, right? That audio model converts that into audio. That audio script is sent back to you through different post requests. That's what you hear on the call. This is one long workflow. Now you replied something back. That input again has to go. It has to update in the feedback of that model. And again, it has to reply on the basis of that, right? So this is an example of a workflow that's established for that agentic AI. In between, it will also need to store a database to store the contextual relevance of what you're saying in a long conversation, right? Or maybe I contacted it before, it needs to query the data for that as well, right? Imagine you have an employee management system, imagine you have a chatbot HR. Now, HR needs to know what happened in the last conversation. You need a database for that, okay? You need Postgres, you need something, right? So that's what a workflow is. Was I able to explain it to you guys to some extent? Anyone?
Yes,
Did I
sir.
went too fast? Was it too confusing? Was it too confusing, guys?
No, sir. No, sir.
Yeah. Okay.
Okay.
So
So I
uh,
think this is a good point. I would like to call up here to invite Rishabh, who is co-speaker for this event, and he'll mostly walk you through to Agentic AI and everything. I'll just be there on the side and assist as of course, right? Please take over the stage again.
so now I introduce Rishabh to please walk through generative AI and agentic AI. So
Thank you
Rishabh,
so much, Abhay. Am I audible to you all? Please confirm once again.
yeah, you're audible.
Thanks a lot. Thanks a lot, guys. Uh, is my screen is visible to you all? Please confirm this as well. Is my screen visible to you all?
Yeah, I think it isn't.
Not yet.
I
Not
don't
yet.
think so. Yeah, Rishabh, we can't see it.
Okay, just a second, guys. Just a second. Is my screen visible to you all now?
Yeah, it's visible now.
That's great. That's great. Guys, I just want this session to be more simpler way, just because I just saw that there are so many students, but they are not able to interact with Karthike. Just because Karthike is more towards the research guy, and they are trying to explain all these things in quite more detailed format. I just want in the audience that, guys, can any one of you please unmute yourself? I just want a to and fro motion interaction from you guys, if is it possible from you.
I think they'll catch up on the way, Rishabh. You can start. I think
Okay,
they're interactive enough. Yeah.
okay, that no issue with this. Guys, before starting towards the agentic AI or MCP tools or MCP servers, have you heard about MCP servers? Have you heard about anything related to agentic AI or a generative AI? Just want to know. I saw that someone is typing over here, Vivek. Not about agentic AI. Okay, guys, no issue with this. Before proceeding with this, I just want that. Can you guys give me a countrywide breakdown? Do you have any idea about that? Uh, the global sources that what the particular country wants to do in the terms of AI and agentic AI, including the major players. I just want to know in the terms of investment, in the terms of policy trends, which country is giving them better idea about the agentic AI, or which country is doing more far better in agentic AI or anything else. Can anyone please unmute yourself? It's more better for me to interact with you.
I think Rishabh, you should start with it. Maybe when they get curious about the questions you're saying, right?
Okay,
Then we'll hear
understood.
some answers
S-
out.
Okay, guys, do you have any idea about China or USA? That just few years back, China is not surpassing the USA, but the current scenario is totally different. That the China is more towards the AGI. Or do you have any idea about artificial superintelligence? I think Kartike have told you all these things in more better format, but just want to know, do you have an idea about artificial super intelligence? Just because on that basis, I'm trying to explain all these things. I have an idea that you get these points or not. I just want that. Okay, understood, understood. Guys, just want to know which model you are basically using, or GPT. Do you have any idea about Omni? Do you have idea about Cloud or a Gemini? Yes. Okay. Saket told me yes. Okay. So, Saket, which model you are basically working on? Cloud. Okay, that's great. That's great. One of my favorite. Great. Gemini 2.5. Okay. Okay. Great. Any Twitter fan is here, guys? Any Twitter fan?
Yes,
Okay,
sir.
great, 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 great. Can you just tell me which model it is? Grok, Grok. I, d- I hope that you don't use Grok for a customer care agent or a customer care support. It was hilarious. Grok 4 is more better. Grok 3, do you guys see that Grok have a hilarious or having an issue with Grok 3? Sakit, yeah. Okay, great, 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 yeah. Great. Okay. Guys, do you have any idea about SEO, GEO, or AEO? I just want to know first, just want to create an environment about these terms. Okay, that's great. It means that you do not have an idea about SEO. Do you don't know about SEO? It's search engine optimization. Now the current scenario is different. Now the things are totally different. It's more about AEO, engine optimization, and we also have a GEO, generative engine optimization. Okay, no issue with this. No issue with this. Any European fan who is working on a, okay, actually short from get confusion. Okay, okay, okay. Guys, any European fan or any Indian fan? Yes, background now. SEQ, SEO, okay. Basically list website on a search engine optimization. Great, great. Okay. Okay, that's great. That's great. So guys, do you use Perplexity? Have you ever used Perplexity, Comet? Perplexity Comet किसी ने use किया है? Yes, yes, great, great, great. Uh, I generally use this for email marketing, but try to come up with a point that never give your credit card details to that Comet. Best for research, right? Uh, it's more about. Are you talking about Saket Perplexity? Okay, now I get the point that where I have to start from this. S- Guys, do you have any idea that today we are surpassing the human brain's interconnections in the form of neural network? It's really a billions of connection we have. And if you see that today's scenario, we have a ANNs and billions of neural networks over there. Do you guys any idea that which architecture is come up with this point and what architecture is come up with behind this? I think Karthik already told you about this. I just want to know that the model you are using, which architecture comes behind this?
Could you go ahead,
Transformer,
could you go again,
transformer.
Rishabh? Yeah,
Sorry?
Transformers. Yeah.
Yeah. Okay, that's great. It's T of GPT, right?
Asim,
Transformers
could you
model.
repeat your question? I think
Guys, do you have any idea what model architecture behind this GPT or behind the models, LLMs models? Now I think you get the question. Okay, okay, that's great. That's great. I get the point that Saket told us that it's a transformer, right, Saket? Saket, just before starting this, I'm just trying to explain all these things. Just suppose I have a point. Is my screen is visible to you all, right? Guys, this is a page of a GPT 3.5. May I get the point? Please use your calculator and try to solve this, the toughest question which I asked to the GPT 3.5, which is a 235 into 5678. Is the answer is right or wrong? Guys, may I get your point that answer sahi hai ki nahi hai? Please tell me that whether the answer is right or wrong.
Yeah, Rishabh.
wrong.
Let's wait for them to. Yeah, I think Rishabh, you can move forward.
Okay, understood, understood. Uh, Guys, the point is that model have stateless knowledge, and if you see the current GPT-5, they have a tools access. But if you come up with a GPT 3.5, GPT-4, then they do not have a tools access. That's why when we ask uh, to solve the what is 235 into 5678, at that time you get the answer is basically you get the answer wrong. So I would love to add one more point that generative AI is different from agentic AI just because there's a short gap you felt in the terms of agentic AI alone model can't do work properly. Or I would say, and why this is come with a point that due to the tools access. As do you have any do you guys any idea about the tools, binding tools with the agents?
Guys, you can type it in the chat or you can speak as well. So Rishabh, I think they don't have any idea. You can proceed.
Okay, understood.
Yeah,
Just a
Abhishek is
second,
saying
guys.
actually the multiplication is right except the first sum. All is correct.
Okay, okay. The point is that Abhishek, they do not have a tools access when you come up with a GPT 3.5. At that time, they do not have a tools access. That's why. And here is the main difference which comes under the generative AI and agentic AI. I'm just trying to explain all this thing in a very light or in a simpler way that you guys get the point. Just suppose when I ask GPT what is LLM, then at that time GPT told me that LLM means master of law. Is he correct or not? I just want to know. Please interact me just because I'm trying to explain all these things in very simpler way. Just because if I'm trying to explain all these things in more broader way, in more tougher way, then I think you guys are not able to understand what I actually want to say. Yes, in one word, it is correct. Okay. or I would say that without context it would be correct. If I'm not able to give the particular context in GPT, then I think it's correct, right?
Yes, sir.
Great, great. Just a second. I don't think so. Why the problem is comes here? Yeah. So, guys, do you guys have any idea about agents or anything about the models, about the tools, about the memory? So I would say that agents are nothing but an application with four main components, and it could be a model, and it could be a tool, or it could be a memory, or it also be a model-based reasoning planning. As you see here, if you see my cursor, that here, whenever a user asks any query to the particular agent, here the agent first orchestrate in a manner that we get the profile over there, we get the memory, and you also learned that we have a short term memory, we have a long term memory over there, we also have a tools access over there, and we also have a model, which model we are currently working on. So I would love to say that without these model, without any of the single component, we would never say that the model is uh, an agent basically. Am I able to explain you all?
Yes, sir.
Okay, that's great. That's great. Okay. Guys, do you have any idea about LLMs?
Yes, sir.
Can anyone explain me what you actually have an idea about LLMs? LLM से क्या पता है?
LLMs are nothing but they are large language models, sir. So best example for LLM is ChatGPT. So we train LLM with larger and larger data sets. So likewise, if we give any prompt or something, it would, you know, return the output.
Great, great. LLMs are basically it's not only the chat GPT, all the models you are working, just like Cloud. Do you guys come up with a model? Facebook का किसी को पता है? Guys, do you have any idea about Facebook कि Facebook का मॉडल कौन सा है?
So like, how are you asking? So initial, initial idea of Facebook, are you asking or something? Could I be more clear, sir?
Uh, Actually, I'm asking about the model. Yeah, Saket, right. It's Llama. Saket, I think Saket is typing something. I just want to add कि Facebook ने अपना जो current अभी open source था, इसे close source कर दिया है. Guys, do you have any idea about this? Okay, that's great. Understood. So, guys, LLMs models are the AI models that trained on a huge amount of data or a textual data, we would say, that it's tried to understand, generate, and mimic like a human language, or we would say that it could be a reasoning with humans language. And where the key features, I would say that it uses the transform architecture. I think Kartike were explain all these things to you, and now I would love to add few of the limitations that it may hallucinate, and there's also a fixed context window over there, and does not understand what is the consequences over there, and these are the some limitations about the large language model, and that's why we are coming with a agentic AI part and try to learn how the agents work basically. Guys, do you have any idea that the current LLMs models work with which part? Basically, I just want to know कि कौन सी learning है. Is it supervised learning? Is it unsupervised learning, or is it semi supervised learning? Self supervised learning, right, Saket? Right. So the point is, guys, can any one of you tell me that it is a supervised learning or a unsupervised learning? Just means that the current image, as you see that here is the cat image in the input part, as well as here is the cat image in output part, and here we have a block, and from the input part we would say that this could be converted into output as a fully image of a cat. So just want to know, it comes under the, is it the label data or not? I just want to know. सिंपलर टर्म्स में बात करते हैं, ये लेबल डेटा है कि नहीं है? Okay, but in some of the cases, I guess these are turns to be in the reinforcement also. Correct, correct. But the point is, key, I would love to know that the current scenario is more towards the, is it supervised learning or is it unsupervised learning? Supervised
Yeah,
learning. Anyone more? Okay. In simpler format, I would say that here, as you see, there is a mask over there and there is a random square over there in the cat image. As an input model, I would say that there's a missing patches you see, and we have to generate the missing patches after seeing the output of the particular image. And we would say that by using the output, we can generate the input. So it's a labeled data. That's why we would say that it's a supervised learning, or it's a part of a supervised learning. Am I able to explain you all? Yes. Okay. That's great. That's great. Great. So also the part here we have a self-supervised learning, that as you see there is a huge amount of textual data we have, and it's come up with a point that we have a land graph Wikipedia content, as we see. And by using this textual data, we would try to convert this textual data into a format that is labeled data. Just suppose we get the input as land graph is, as a land graph is a input data, and after that land graph is a, a powerful, it could be an output data. So we generally come up with a point that we use this textual data to convert this into a tabular data, and or we would say that it could be converted into a input output stream or a key value pair. That's why we would say that whenever a model learn itself from itself, then it could be a point that where we would say that it's a self supervised learning. Understood or not?
uh, yeah, Rishabh, you can proceed.
Guys, also there is another example of self supervised learning, as we have a discriminative AI and we have a generative AI. In the case of discriminative AI, as you say that there's a training data, and in case of discriminative AI, we would say that uh, either the image is trained, and we would say that we will define this 1 or 0, that either it's labeled as a 1 or either it's labeled as a 0. Whether the data is 1, then we would say that the particular sampling would be given, the value is correct, and whether the output is 0, then we would say that the predictive value is going to be prediction value could be converted into 0. So But in case of generative AI, it could be more towards that how the generative AI basically asks how these things happens. Generative AI generally asks the particular model that whether the data is whether the given data is correct or not, or also ask particular guys. Yeah. So I would
Yeah, Rishabh,
add. Yeah.
I think your audio broke after some point. I think we should start again with generative AI, I think.
Okay. Guys, am I audible to you?
Yeah, now it's working
Yeah,
fine.
yeah, it's working fine now. You can
In the
proceed.
case of generative AI, it would always ask that how they learn, and we would say that it's more towards the part of a representational learning over there. In case of generative AI, we would say that it could be a fit arena over there, that how the image is basically generated over there, and we would say that it could be more towards the minimizing the error, and training part could be increases over there. Is it clear to you all or not?
Yeah, if you feel any doubt in this, you can ask, or we can repeat that part as well. Yeah, I
Okay.
think Rishabh, please repeat this.
As in in the case of discriminative AI, the data particular data is format that whether the just suppose I'm just trying to explain this thing in a more simpler way. जो भी पर्टिकुलर ट्रेनिंग डेटा रहता है वो पर्टिकुलर ट्रेनिंग डेटा या तो जीरो रहेगा या तो वन रहेगा इन केस ऑफ डिस्क्रिमिनेटिव एआई we would say that either it could be zero or either it could be one, but in case of generative AI the first question comes under that कि जो पर्टिकुलर इमेज है वो पर्टिकुलर इमेज बनी कैसे है वेदर आई एम जस्ट ट्राइंग टू एक्सप्लेन दिस इज मोर बेटर फॉर यहाँ पे जो फॉर्मेट यूज होता है वो को रिप्रेजेंटेशनल फॉर्मेट का यूज होता है, मतलब रिप्रेजेंटेशनल लर्निंग होती है. एंड इन केस ऑफ रिप्रेजेंटेशनल लर्निंग हम ये चेक करते हैं कि जो पर्टिकुलर इमेज है वो बनी कैसे है. जस्ट यहाँ पे ये जो इमेज देख रहे हो, इस इमेज में ये जो लड़की है, इस लड़की के स्पेक्स को एकदम प्रॉपरली फाइंड आउट करना, साथ ही साथ जो हेयर का कलर है वो फाइंड आउट करना, एंड यहाँ पे जो बिल्डिंग ब्लॉक्स बने हैं इन बिल्डिंग ब्लॉक्स के कलर्स को फाइंड आउट करना, एंड साथ ही साथ जो ब्लॉक्स हैं उन ब्लॉक्स की साइज क्या है, लेंथ क्या है, ब्रेड्थ क्या है. सो इन केस ऑफ जनरेटिव एआई जो सबसे पहला क्वेश्चन आता है कि ये इमेज बनी कैसे है, हाउ द इमेज इज बेसिकली मेड. सो ये जो पार्ट है ये पार्ट रिप्रेजेंटेशनल लर्निंग का पार्ट है. एम आई क्लियर? क्या मैं क्लियर कर पाया? ओके.
Karthika, you can add your point if you want to.
I just want that कार्तिकेय there is a option of transformer. So कार्तिकेय थोड़ा और better तरीके से बता सकता है.
Yeah, I
Yeah, I
think
think.
I'll take up from here. So, can you shift to the next slide, Rishabh? Yeah, okay. So, I think the architecture Rishabh was trying to tell you was of GAN. I'm just repeating that. So, it was GAN is known as a generative adversarial network, right? Basically, what happens is you've got a generative network and you've got a discriminative network. So, what happens is you feed some input data, right? And the generative network, let's say, creates some new images on the basis of the training sample it has. Now, the discriminative network's task is to classify if an image is a training image or if it is a new image, right? And whatever classification it gives, that again is sent to the generative network. So they act in a sort of a positive feedback loop to each other, right? One keeps generating, one keeps telling fakes, one keeps generating fakes. So one is a fake maker and one is a fake detector. And in the process of doing this, they both train each other, and this is how they work. Now that was about GANs. Now let's learn about what's generative and what's discriminative AI. Okay. Basic difference, a very basic difference. Generative AI models learn the probability function. Okay. You even in LLMs we call them predictors. How are they predicting? They're predicting on the basis of probability. You have a probability distribution across different sets of embeddings. Then you choose the most probable thing from that. Okay. And same in discriminated networks, however, you draw decision boundaries, right? You learn a specific decision boundary that, okay, this is the decision boundary. Beyond this, it is this. Before this is this. Very simple example would be a classification algorithm that achieves a decision boundary, right? A support vector machine, it achieves a decision boundary in a n-dimensional hyperplane, right? In generative networks, you don't have a decision boundary sort of thing. Imagine a discriminative network has a strict line. There's a wall, right? Here it's this, beyond this it's this, right? And in generative network, it's kind of like a probability function. So one probability function is coming from there, another is coming from here, and they intersect at one particular probability value, at which phase it's difficult to determine what that particular data point corresponds to. Okay. So let's say it has a 0.3 probability of being this, and it also has a 0.3 probability of being the other class, right? So which class does it belong to? That comes in generative networks. As you can see in the graphical representation here as well. The generative, it's like different gradient slopes. If you are familiar with this stuff, kind of architecture, we use this to represent different landscapes, right? So the bluer or the redder it looks, the more higher it is. That means the more high the probability is there for that particular class. And the shallower or the lighter the color looks, showcases the lower probability. And at some point, you can imagine them intersecting with each other, right? So that's basically what generative AI does. It learns probability distributions. Okay. And in discriminative AI, you can see, as I said, a strict decision boundary. Can we move on to the next slide, Rishabh?
Karthik, I just want
Okay.
to add few of the things in a transformer architecture is more about that.
Mm-hmm.
I think it's core more easy to understand these guys about the tokens, about the embedding systems, and how these things are converted into the vectors. So I have one more website that as I gone through. I just want that you take over this and just try to explain these things to these guys. Just a second. Please repeat again. Sakit, what do you want? Can you just tell me?
Yeah, I think that was a previous chat. You can
Okay,
move
okay,
forward.
okay. Yeah. Karthik, I just want that, guys. I just want you have an issue with transformer, right? How the transformer architecture works. May I get to know?
Guys, you can react on this.
If you have an issue, anything, I just want to try to explain all these things in more simpler way. That how these things can be done. We have a tokens here, and we also learn how the embeddings could be work, and how these embeddings converted into vectorization, and how these vectors basically try to explain about the architecture of a transformer.
I think they have understood the transformer part. You can, I think, Rishabh, you can proceed with the agentic path.
Okay, that's great. uh, Guys, just want to add few of the points here that in the generative AI, or you would see that we have a just suppose we have a text particular here. This is how it works. We first converted those texts into the tokens. Have you heard about the words tokens previously? Just wanted to know. If you do not have any idea about the tokens, I would love to add that the words could be a 3 by 4 of the tokens, and I just try to explain these things in a manner with a one of the website. It's called tick tokenizer. Just see that we have a sentence, and first these sentences are converted into the tokens, and these tokens now converted into the nearby words, and we would see the graphs over there. Yeah, thanks a lot, Abhay, for giving the tick tokenizer over there. uh, so along with this, I would love to share this page to you all guys, that you get the reference how the basically tokens and how the basically these tokens are converted into the embeddings. And embeddings are nothing but it's a numerical array of a semantic or systematic meaning of the words. And how do we capture these things? It's more towards the word. I think you guys heard about the cosine values particularly in your school time. Have you guys heard about the cosine or sine value
Okay. I,
in your school time?
I think what Rishabh is trying to explain you here is trying to show you how the embedding vector, right, for that particular word or token, as I mentioned, is created on the basis of the nearby words it has, right, across different dimensions. So while pre-processing the tokens, what usually happens in NLP is that you don't give different words with similar meaning with different token values always. Reasons, first of all, then you have a lot of embeddings. Secondly, then you might not be able to always catch the contextual relevance. For example, I might say, I like that guy. He might say he loves that guy. Or they might say that they are sort of aligned with that guy, right? Now, the context in all three sentences is sort of similar. But if I keep the word like, love, etc., right, with similar meaning, or at least I annotate them, it's called, so there's two ways to do this. One, in one, you put them back to their linguistic meaning, right? And in another you just cut off the sentences, right? So these are two different. It's called stemming and lemmatization. In lemmatization you go to the lemma or the grammatical meaning of the word, and in stemming you break down the words. You have just specific rules. You've got porter stemmer, you've got lover stemmer, and a lot of other algorithms. Just take the word, you chop it down. Okay, so like one rule is you remove the ing from the word. Okay, another rule is if you have double s, you make it into a single s. If you have ss yes, you make it into ss, right? Or if you have just s, let it remain. So these are some couple rules that it has. Stemming has. Lemmatization is more accurate but more time consuming, etc. But these are just word pre-processing stuff. When you have a sentence, you break it down to tokens. As I said to you, right? Token can be a part of a word. Word may have different tokens. It might also itself be a token if it's small enough. Now those tokens, they are lemmatized and stemming is done on them. After that is done, then they are converted into vector embeddings, right? Through different methods. And once those embeddings are achieved, they are then sent to the transformer architecture. And as you can see in the representation, it's also showing how embeddings of similar works are similar, right? So train is at the same place as bus or car. College and school are same place as work. Basically, a place where people go through, right? Walk, swimming, and run are placed around the center, which means their activities, right? So kind of a grouping. As I said, king will be more similar to a male, queen will be more similar to a female, right? These kind of things. A queen might also have other meanings. It might have chess related meanings. It might have ant related meanings, right? So that might also be there. It might have meanings related to the queen's band, right? The one who said, "We will rock you" and other songs, right? So this all is done there, okay? And this is what's reflected in the website. I think you can check it out. We'll drop you the link for this, and we'll do with this. This is a cool way to see the self attention and other architecture. And at this point, I think we'll move ahead with the slides because we are on a time crunch. So can we go back to the slides, Rishabh? Okay, yeah, I think we have had enough on. Yeah, let's just come to temperature and stuff. So, what do we mean by temperature? Okay, you remember me saying LLM is called the next word predictor, right? It's a very good next token predictor. So, how does it decide which token to predict on again? Because if you remember something I told you, it feeds the word and in the end of the day, you get a vector, right, as an output, जिसको de-embed करते हैं. Now, is it necessary that that vector is the exact value of some word? It's not, right. It's a continuous thing. It might be different. So what you do here is through some sort of similarity functions, you determine the vector that it has outputted to what word it is similar and to what extent. On the basis of that, you assign probabilities to those words. That okay, you're trying to say that LLM is giving out to you some random number out of we are trying to guess here. We built in mathematical algorithm to guess that okay, which word is it trying to predict maybe? Okay, so for example, if a guy comes and says to me that okay, I have a fruit, it's red, it's crunchy, I might be guessing it's an apple. It might not be, it might be something else, but I might be guessing that, right? So it's sort of that you assign probabilities to different words, right? Now, after assigning the probabilities, you have got something known as temperature. Okay, what does temperature do? Imagine a Gaussian distribution, a bell curve. Okay, if you see these graphs, now what you'll see is the red graph is a flatter Gaussian, while the blue graph is sort of representing a sharper Gaussian. What happens with temperature is temperature usually ranges the value of 0 to 2, right? If you keep the temperature 0, always the word with the highest probability of that was determined using similarity will be chosen. For example, I'll always choose apple. Okay. And if the temperature is very high, let's say 2, the highest limit, now every word has equal probability. What am I effectively doing? I'm flattening the Gaussian. Okay. So now what will happen is apple is as likely as banana, as likely as grape, as likely as anything else, right? This is what is happening here. So this is what temperature does. That's why when dealing with GPT, this is just a tip. If you want it to be more creative, keep the temperature high. It will give you more creative outputs, more creative stories. If you are doing some kind of mathematical task or coding task, right, then I would suggest keep the temperature low. That way, its output is more strict and rigid and based on its training data. It doesn't mess around with stuff. When you give it high temperature, it will try to mess around with stuff. When you give it low temperature, if you try an experiment, you'll see it will repetitively give the same or similar answer to this question, right? And if you make the temperature high, it will give different things. So basically, this is what temperature is, right? Apart from this, there's another way of selecting the what word it's going to predict. It's called top K. So what it does is that it doesn't choose from all the probability distribution across all the set of words that are in the set of words that we have. It chooses only from the top 40, let's say, words, right? So it says top K. That means top K words. And from those words, a probability distribution will be drawn and the words will be chosen. That's one way. Another way is top P. What it does is it selects the probability threshold that, okay, I'm going to take the Gaussian till this probability threshold. Let's say pointed. If you set the top P equals to 1, that means all the words. If you say top P equals to 0.001, that means only the highest probable word, right? So that's how that things figures out, sort of. Okay. So these are just different ways of configuring how the LM outputs behave, right? And as you can see here, we have token probability assigned to each token. What is 1 plus 3? Now you give it to LM, it determines, okay, 2 is this probability, 3 is this probability, car has low probability, TV has even lower probability, ship has even lower probability, right? So this is what it has learned. So you can, I think in earlier versions of GPT, you could have asked it to show the token probability for some top 10 or top 15 tokens or so. I'm not sure if that feature is still available, but yeah, it was there. Can you move on to the next slide, Rishabh? Again, so this is trying to tell you something. Okay. My question is different. Okay, Saket has a question here. Words, there's multiple conjugations, let's say 4 spaces. Will it create extra tokens or get normalized? How do common tokenize it? Okay. Uh, as far as I'm aware, white spaces are generally dropped. So you drop the white space to the extent that you only have one kind of white space characters, so you don't have extra redundant characters, so to say. Okay. So I think that should answer it. I'm not sure if how accurate I am because different models might also deal with it differently, right?
Actually,
Again,
Karthikeya, in this
depends.
in this slide, it's more about
Yeah.
the chip that the GPT is stateless over there. That's why the memory
Oh yeah, no, I
component is
understand.
shown. Yeah.
Okay. No, Rishabh, I understood that. I was just taking over Saket's question. He
Okay.
asked you that he has I love Apple and he has I love and space Apple, right? He's asking what do we do with white space there? So that's what I'm saying. Different models deal with it differently, but I think what they predominantly do is that they remove the white spaces and they deal with the tokens separately. Yeah. I think if you take any NLP course, it would be very helpful. It will tell you how tokenization and everything happens. Okay, so now, as I said rightly said, this tells you LLMs are stateless, which means LLMs don't remember anything. Now, you might ask me conversely that Karthik, you're saying you don't remember anything. Yet, if I'll ask GPT, how do I look like, or what did I ask just before, it will answer me. How is it doing that? Great question. I'll tell you how it's doing that. So, what happens is when you do, and this can be seen if you do API equivalent to a direct LLM because then you have access to the actual LLM. But when you're accessing to the Chat GPT's website, right, or through Gemini's website or something, so what happens is whenever you type up something, okay, you send one input prompt, you get an output prompt. Now LLM won't remember the conversation that just happened, but the next time you provide it a new input prompt, you assume ki it has the context, right? But how the website does is it takes the input prompt that you sent earlier, the output prompt that the GPT sent earlier, it appends them and it might summarize them before appending them or something. But in a very rudimentary case, it might in a very rudimentary case, it might just append them with your second input, and it will send the whole conversation back again to the LLM. So that's how it's having a conversation and it's having the context. In a very long conversation where they fear that the input token limits might surpass, they just summarize the whole thing. And if it's surpassing altogether, right, you might notice something that they're they provide different limits for different tiers, right? So you also often, I think you would have noticed, sometimes ChatGPT says, okay, chat's token limit or something expired. Please create a new chat, right? I think you guys have had those requests. Have you had ever that experience? Anyone? Anyone that has had GPT saying yeah. So this happens because I think you have, from my understanding, you have expired the contextual limit in free tier, right? That okay, you are providing us so many tokens and it's storing them in its memory, it's storing them, sending them again to the LLM. So you have expired that thing. So it retracts that. Okay. So that's what basically happens. Can we move? So that's this basic meaning of telling this is when you're dealing with LLMs with API calling, right? You're dealing with the actual model. The model will be stateless. So it's a point to remember while creating agents. Make sure you have some sort of implementation for creating a contextual memory so that you can send the earlier chat as a summary or as the exact input and output prompts itself to the LLM so that it can answer you with regards to that context. Otherwise, it will not remember. It will not remember. It does not remember the conversations. Okay. Yeah. You can fine tune it so that it knows how to answer different questions, but fine tuning is expensive. And again, it doesn't exactly recreate a memory because LLMs are, as I said, and as Rishabh said, stateless. Okay. Now we're coming for a RAG architecture. So this is an actual architecture for an enterprise RAG, but I'll just basically explain you what RAG is. Remember, I think ChatGPT launched in 2020, right? If you remember at that point of time, whenever you used to ask it some question or something, right? It used to say, I'm only trained for data till September 2021 or something, and I can't answer beyond it. Did it used to say it or not, right? I think everyone will remember that, right? Nowadays, if anyone uses ChatGPT, it also gives you web documents, right? And other stuff. It can also answer live questions. You can ask it, okay, what's the temperature in Varanasi right now, right? And it will answer you. How does it do that? You have built a sort of a retrieval augmented generator with other API callings as well. Okay, so what is a RAG? Basically, RAG gives the generic LLM an ability to answer a specific question. RAG is a very simple workflow. You send a query to the LLM, right? LLM searches the specific knowledge base for documents similar to that query. You've got vectors for documents as well. You've got a query vector. You do similarity matching, whichever documents come similar. Those documents go with the query again to the LLM. Now the LLM has this whole thing as a context. It takes this and then it outputs back you the answer. So this removes the hassle of fine tuning and makes the LLM be able to answer more specific questions, right? For example, you wanted to answer questions related to some legal arbitration. Okay. Now you give the arbitration documents as a knowledge base, and when it has those, it can answer your questions. So that's what a RAG is. That's why it's called retrieval augmented generator. It's retrieving documents from the knowledge base. It's augmenting the query and it's generating on the basis of the augmented query. This is what we mean by a retrieval augmented generator. As you can see here as well, you have got document ingestion, you've got storage, and so what basically happens is you have a retriever, right? And then it goes to encoder, retrieval is done of the documents, ranking is improved, it goes to generator, it goes to a guardrail so that it does not output something that should not be given as an output, right? Get the final response, send back to the storage. Again, you do a lot of stuff, and finally, you give it back to the user. Yeah. Can I move to the next slide, Rishit? Okay. So this is how you are making an augmented learning or a agentic AI, so to say. You're giving it access to tools, you're giving it access to memory. LLM is a stateless machine. You give it access to tools, you give it access to memory, and you can create agents. Okay. What do we mean by tools? When you coding, tools just mean functions. Calculator function may be a tool. A function that can do API calling may be a tool. It's just a name. The tool, this word, no. This word was brought out by, I think, Google tool calling. Or I think Anthropic did the tool calling thing and Google calls them functions or something. They have got this different, how do I say, different lingos for the same thing. But yeah, it works like that. So that is there. Okay. Can we move to the next slide? Okay. So here again, we're talking about long-term and short-term memory for the LM, right? So for short-term memory, you can give it as it is. For long-term memory, again, it's very long. You might expire the token limit. You can't store it in cache. So you do two things. First, you store it. Second, you summarize it and then send it to the LLM. This is just a gist of what this slide is trying to explain. Next slide, please. Again, now we are having different embedding models for different conversations. Now you've got different vectors for those conversations which are stored in the vector database so that you can retrieve those conversations more effectively. Can we go to the next slide? Again, this it creates the same thing. So you have got a vector database. This is a RAG architecture and all. So this is basically what an agent does. Again, we have a definition here, right? An agent is anything that can be viewed as perceiving its environment through sensors and acting upon the environment through sensors. Basically, an agent to take an action on the environment, given its tool and memory, it should be able to do some sort of planning. Given an environment's perception, it does some planning on the basis of the tool it have. It takes some action, environment again gives some perception or something. It updates its memory, it plans again, it uses the tools it has to use, again action and so on and so forth. That's how an agent behaves. That's how we behave as humans, right? Whenever we are supposed to do some task, we determine that okay, we have to do this. We plan for it and we execute it. We get some feedback, right? We modify our planning according to that feedback. We update our memory that okay, this happened, and then we again act for that instance. Again, we get that, and we keep on doing this until we reach sort of a state where we can complete the task, right? And this refers to the agent autonomy. So how much autonomy the agent has, right? So in the first, the topmost column, you have got LM, you give it a prompt, it gives you an answer. That's very less autonomous, almost no autonomy. Then you have got fixed steps that, okay, please do a vector search for this prompt, get some knowledge based documents, give them to the LM, please answer on the basis of that. That's RAG. That's a controlled autonomy. And then you've got perfectly autonomous. You give the prompt to the LLM. LLM plans something. It takes the action according to those plans. It might summon other LLMs as agents. It updates the plan again, takes the action until it finally determines that okay, the action is ready to be sent for an answer. Right. And this is what you call an agent. An agent is an autonomous thing. Can we move to the next slide, Rishit? Okay. So I think now we have come to the end of this session, and we would want to explain to you guys about what Aureeture AI is offering you here. Why are we organizing this session? The why of all things. Why did we do this, right? So, Aureeture AI is a career guidance co-pilot startup. Right? It offers you primary product as an AI co-pilot, which will act as your dynamic, personalized coach to help you achieve your career goals. It will tell you what to do in case you're confused, how to pursue different career lines, so on and so forth. Right? It's like your friendly senior that not everyone has. It will, through its boot camps, we have boot camps in offline or online format that you guys can attend for a nominal price, which will offer you sessions by industry professionals who are already in job profiles that you might look for, product managers at high labs, software engineers at Google, so on and so forth, right? They'll conduct sessions, they'll walk you through their maps, how they figured out their field, what's the nuances of those fields, right? You've got real life industry projects in collaboration with corporates so that you get to build actual stuff, so that you get to know what industry is actually working on rather than just pet projects, right? You've got sessions on on LLM based tools so that you can do your work faster. You've got sessions on ML, you've got sessions on product management and all other stuff, right? So that you can get a basic understanding of all sorts of fields available for you, right? And you can, on the basis of that, select a particular career path at which stage ORHS app and ORHS Copilot will also come into stage and will guide you step by step through your career journey, help you achieving, help you in achieving your goals. Will offer you a competitive platform. These are all future releases where you will have life challenges. You'll have a gamified sort of healthy competition, right? So that you can also see how your peers are doing, how you are doing on a personal basis. As we always say, compete with yourself, right? And you've got structured learning paths as well that, okay, if you want to become an ML engineer, let's say, please follow this roadmap. If you want to become a product manager, please follow this roadmap, and so on and so forth, right? And this is basically what Aureeture AI is offering. So this is about Aureeture AI. And this is, I think, this is why I think you should, I think, regardless of the point of life you have, while we are primarily aiming this product towards the 10th or 12th students, right? And for the college first year and second grades, I think regardless of which career point you are at, this might be a useful product for you if you're trying to explore a new career path, if you're trying to do a switch, right? If you just want to help continuing your career path, right? So we'll try to offer you that. And I think Rishabh and Abhay can elaborate more on that. I'd like to invite them on the stage. Right.
Yeah, yeah, Karthik. Before we talk about it, Saket has a question. As a cybersecurity researcher, my last question is agentic AI systems acting on their own. So, what are the biggest security risks we should watch for, and how can we build strong protection to stop bad actor from exploiting these AI? So basically, that question, if I summarize it, it's basically on how we can um, stop people from exploiting these AI tools and the upcoming agentic AI systems.
Yeah, I think Saket, you are really on point because this is a big vulnerability. In fact, I know people who are working as AI security researchers, right? And they are trying to figure out this field as well. Often, a very good way to break a site's or a company's security is through the chatbot they have implemented. It might be okay. So one popular exploit was that the MCP tools have a right. So MCP itself does not have any problems, but if you configure it wrong, right? That's when you do have problems. So one solution for this thing was please do not take GitHub MCP implementations. They might have bugs in them. They might, when you're just doing normal MCP tool call, they might just transfer all your chat content, all your API keys back to the hacker that just posted it on GitHub and we just took it up freely, right? So that's one thing that might happen that you need to secure up. Another thing that you need to be sure of is that when you are giving these models out to interact, right? These agents out to interact with your consumers. You need to be sure that, okay, they do not say anything that's not meant to be said, whether it be confidential data, right? For example, if you're a medical startup, please do not tell them the customer reports. That's a basic, right? It might have access to the customer reports. Please don't tell it. Don't tell them how we are implementing our architecture and stuff. So for that, you need to implement guardrails, right? For example, Google offers a guardrail product. It's based somewhat on named entity recognition, right? So it identifies what the LLM is saying. Is it safe to send it there or not, right? And usually with LLM API accesses, you do get that, and it also tells you, okay, this is the toxicity of the prompt, this is the adult content of the prompt, this is that, this is that. And one more thing that you can do is blocking the harmful prompts. Okay, that is very necessary, and I guess implemented by all. That's also what you see in ChatGPT when you give it a harmful prompt, it says, I cannot answer, right? Now, there's two way of doing that. One way is that you give it a guardrail. The guardrail stops those things. Another way is you train it. Okay, you train it to do that. This prompt, please answer this. This prompt, please answer this. This prompt, please answer this. That's one way that you put it in the training. Another way is putting in the guardrails. I would suggest do both, right? That's another thing. You there's there's a lot of risk. You've got prompt injection, right? You've got unexpected behavior. Your LLMs might start saying unexpected things to your consumers. You've got propagation of attacks. Resource depletion can happen, right? For example, if you just gave me unlimited API access, right? That okay. So there's other startups that they have given us tools. I won't name them, but so their LLMs, they are not very good with this guardrails and stuff, right? So they have just given out direct LLM access of GPT-4o, and you can ask it basically anything that's not even related to their field. And I can just burn their tokens away like that, right? Because every prompt I sent, it's burning the cost for that startup, right? That's also a risk. That's a risk that we need to analyze, right? So need to consider that. So you need, first of all, before sending it out, please have researchers who do the prompt injection for you, who do the red teaming for you so that you know how to blue team it. You need, and another thing that can be done is human in the loop for critical action so that if something very critical has to be performed, it goes to a human for approval first, right? So that you do not give it complete autonomy because again, it's AI, it's a machine, it's based on generative AI, right? It's based on a probability mechanism. There's a always a chance it might say something that it's not meant to say, right? So you're playing with probabilities, right? And then there is fine tuning it, is training it on those specific ethical things, right? And then there is also monitoring. You need to monitor the request that's coming to the AI and to your agent, what your agent is doing with them. You need to monitor if something fishy is happening there, right? You need to red team. These are some standard ways you can approach it. Of course, there's other security research as well. So yeah, as I said, zero trust access, continuous behavior monitoring. You need to do these things, right? You need to ensure that your company is placing in guardrails, and you need to ensure that whenever you're using an LLM agent, you are making it trained on that data as well. That okay, please, agar if this wrong prompt is coming, please do not answer it. Block it. Say I can't answer this, right? So that all needs to be done, and that's I think on the headache of the team. Because often what happens, Sakir, I think it's not the LLMs or the agent's fault, it's more fault of the developer who has implemented it. You have an MCP architecture, you just borrowed from the GitHub, as I said. Now that had a bug in it. That bug was exploited. It's the developer's fault here, right? So we need to do all those things. Again, it's agentic AI, it can automate stuff. Very good. It can reduce our workload. Extremely excellent, right? But we need some verification. We can't rely on probabilistic mechanisms to give us deterministic outputs that, okay, this might happen, this will not happen. I think that's part is good there. It's a very nice question, Saket. Yeah, and I hope I could answer you.
Yeah, I think yeah, Kartika, I think you were able to answer the question. And guys, if you have any question or doubt, you can unmute yourself, you can type in the chat. We are here to help you out.
Happy to help, Saket. Any other question, guys? Or should we close the session as we have exceeded the time limit by 28 minutes? I think it's significant time for you and for us as well. So
So I
I
think,
think
yeah, Kartika. So I think
the questions, and
the
after that we can close.
mm, yeah. So before that, we will be sharing a
And
feedback form with you guys.
yeah,
Please do fill the feedback form so that we can improve on the next sessions. And we usually conduct these sessions on different topics. And stay tuned with us. Do follow our social media. I've shared in the chat. And yep, yeah, Karthik.
Rishabh, Abhay, would you like to tell something about Aureeture on the closing note?
Yeah, sure. So yeah, I think Karthika has already told about the vision and the things that we do at Aureature. And apart from this, we are gonna conduct a 3-day workshop. Rishabh, can you please take the slide? Yeah. Um, yeah, okay. So basically, we are gonna conduct a 3-day workshop, which is basically where students or college mates can basically connect with the students, and we have a problem statement from the student as well as the from the industry as well, where student can sit and interact with them. We have career guiders who will talk about these problem statements, guide you with the solutions. You will work with them, and yeah, next slide. Yeah. Yeah. So we have decided that the this will be a 3-day workshop. So day one will be where the teams will be working on creating, will be getting a problem statements. They will be have discussions on them. Then the second day will be basically the teams will be working on the problem statements. Orature team as well as the industry experts will help them refine the problem statements. And day three is basically about a fake investor program where they pitch their solutions to the investors as well as the experts from the Aureture AI team. And so in this way, the bootcamp will be conducted, and we will share the details with you through your mail. And yeah, I think that's it about Orature. And Rishabh, do you want to add anything about it? Yeah, Rishabh, go ahead.
Yeah, I think you guys add all of the things, and I think now the students get the point what we are trying to build. And it's more about the 3 days boot camp. It's a future boot camp where you get the real connection from the corporate leaders. Corporate leaders share their experience to you all, and at the day one we have a grouping over there. You get the problem statement from the companies, and some of might be wants to be become an entrepreneur. So those are some terms over there as well. And day two we use no code LLMs over there to use how basically used to use no code LLMs to find out the particular solution. And if you find out the solution, how to change those particular solution into real time projects. At day three it's more about the fake investor program. All the groups members, all the team members over there pitch their problem statements among the solution. I would say that among the investors, and you get the real time access. And you from this boot camp you get the point that how the career discovery helps you.
Yeah, I think we have come to the end of this workshop. And thank you everyone for staying tuned with us throughout the workshop. And we will update you about the next workshop Stay tuned with us, and thank you. So you guys are free to leave. If anyone have any doubt, they can ask.
Thank you for attending the session, guys. And if you want certificates, you can just pay the nominal price and get them. And we'll be really happy to see you in other future sessions as well. Thank you all. Thanks a lot for attending. See you again. Bye bye. Good night.
Right, everybody.